So in the previous video, we looked at steady state for a first order system. Now we're going to look at the time constant and the gain of the system. Again, we're going to use this CSTR as an example. We have the input concentration here, Cn, which I will regard as our input. So I'll make that blue. And the output, the response of our system, is the concentration of the drain here, of the outflow. I'm going to make that green in here as well. So now let's imagine that we have had a certain level of input for a while. Let's draw that as a graph. So let's say that Cin has been at this level here for some while, and then we changed the input concentration at some point to a new level here. And let's imagine that the response, the concentration of the outflow looks like this. Assuming that we have no amount of substance in the tank to begin with, we start here. And then we kind of approach some level. It might not be that level. Something like this maybe. It doesn't necessarily have to be Cn. In fact, it rarely wouldn't be. So we're approaching some steady state level here. But then what happens when the concentration suddenly the input concentration suddenly increases? Well, a new change will start off. Maybe something like this. At a new level, a new steady state level will be realized. So let's call that C bar 1 and C bar 2, and we can call it Cin1, and this level up here is Cin2. First question I would like to be able to answer is, well, if I change my input by this amount, let's call it delta x, how much does my output, my response, change? So that would be the difference in the green levels here. Let's call that delta y. And more specifically, I'm interested in knowing the ratio between those two changes. The change in steady state response, the difference between the two C bars here, relative to the change in the input. And this ratio is in fact the gain of the system. So basically I want to be able to answer, if I change my input by this amount, delta x, how much is my output going to change? Of course I can rearrange this equation so that delta y is then equal to the gain times delta x. So once I know the gain, I can do this computation and see how much is my concentration, my response in the tank going to change if I change my input. So my input concentration. How do we compute the gain? How do we compute this? Well, the key is, of course, the differential equation that we have here for our system, in this case our CSTR. It's a molar balance. We've seen it before, so I'm not going to spend time deriving it, but this is our differential equation for the concentration. So what we do is that we bring the differential equation to standard form, which means collecting all the terms involving the response variable C on one side, So when I do that, I get I have v dt dt, then I have f plus kv times c. So that was those three terms here, and then I have one term here which doesn't involve c, so I'll keep that on the other side of the equation. Secondly, we divide by the coefficient of the response variable. In our case, the response variable is C, that's the concentration. So the coefficient of C is this one here. That's the coefficient, that's the number which is multiplied to C, multiplied by C. So when I divide by this number, I get a new version of the equation. I can just fit it in here. I'm going to get V divided by F plus KV dc dt plus C equals F divided by F plus KV Cn. Now that I've brought my equation to this form, I can directly read off the gain of this system. The gain is the number that I have here. That's this coefficient here. And how do I know that? Well, that's the number in front of my input variable. Remember, I might as well call this, I might as well write it in blue. Here we go. So the coefficient in front of my input variable, that's the gain. So if I know the flow rate and the reaction rate constant and the volume, then I can compute this number here. Just for overview and transparency, I'm just going to change the color of the response variable into green, like that. Now, the next question we would like to be able to answer is, how much time is it going to take for the response to go from here to the new steady state level? I mean, we came from this level, this C1 bar, that was the level we were at. Then we changed the input level, and then the system responded by changing gradually the concentration. Question is, how long time will it take? Well, the good answer is forever, because mathematically speaking, this function is never going to reach steady state. So we can't really answer that question. What we can answer is, can we find a number so that a certain percentage of the change has been achieved? And the number that we would like to compute is the time constant. The time constant. The time constant tells us the time it will take for the system to achieve roughly 63% of the change going from this steady state level to this steady state level. If we go another time constant, we will have achieved something along the lines of, if I remember correctly, 87%, and another time constant, we will have achieved 95% of the total change. As I said, we're never going to get to 100. That's going to be at infinite time. But after 3 time constants, we will be almost there, 95%. So the question is, how do we compute the time constant? And again, the answer is in the differential equation. We've already brought it to this nice form here. Let's just put a box around that, because that's really useful form of the equation here. Now what we do is that we look at the derivative term here, the derived term, and we look at the coefficient in front of that term. So this number here that I have here, this is actually the time constant, or tau as we like to call it. So if I know the volume, the flow rate, and the reaction rate constant, I can compute the time constant, which means how long time will it take for the system to achieve 63% of the change, or two time constants, 87%, and so on.